Um, we're in section 4.2 of the textbook. We're finally going to learn theorems that let us take limits easily. So far we've just known the definition of a limit, which is, the epsilon delta definition. So you're given an epsilon, you have to find a delta, such that blah, blah, blah. Now, last time we proved this theorem 4.18. And this is really useful because it lets us connect taking limits of functions to taking limits of sequences. And we've already proved all the theorems about limits of sequences. So instead, if we want to show that we've got a limit of a function, okay, we just have to take a sequence that converges to the point, a sequence in our domain that converges to the point where we want to take the limit, and then we look at the sequence of function values. Okay, we'll see a lot of applications of this today. So, basically, today's lecture is we're going to use this theorem to take all the, so these are function versions of section 3.2 results. Okay, so we're going to take this theorem and translate results we already know about sequences into results we know about, or results we can now know about functions. Okay. So we'll try and keep it on the screen for as long as I can, but we'll come back when we need to reference it. So let's start with the situation. This is part of a proof of a theorem, but I just want to specialize to one situation. So suppose, okay, we start with our normal hypotheses. A is a subset of R. C is a cluster point of A. And F maps A to R. But, sorry, I want two functions. Yeah, let's do two functions. So we're going to do F and G, both map A to R. If, and now I'm going to assume we know the limits. So the limit of F at C is L, and the limit of G at C is capital M, then the limit of F of X plus G of X is obviously L plus M, because what else could it be, right? Now, let me first point out we haven't proved this yet. We don't know this yet. We could give a proof just straight from the definition. It's not too hard. But since we've already done a proof of all of this stuff for regular sequences, for sequences, sorry, they're nothing regular about them. Since we've already done a proof of this for sequences, let's just use it, okay? What do we need to show if we want to show this? Okay, so I want to prove this thing. I need to show that for every sequence xn in A minus C that converges to C, the sequence, and now I want to look at the sequence of f of xn plus g of xn. That sequence converges to L plus M. Okay? So let's do it. Proof let xn be a sequence in A minus C that converges to C okay. Now, what do we know? We know the limits of f and the limit of f and the limit of g. And now we go up to our theorem connecting functions to sequences. That means that we know that the sequence f of xn converges to L, and the sequence f of the sequence g of xn converges to M. Okay, so we're going to use that. Therefore, by I have the theorem number up there, so I could easily just write it in, theorem 418, but just to get us all out of the habit, by a theorem, okay, because we never need to cite the numbers here. What I said, the sequence f of xn converges to L, and g of xn converges to M. Okay, that's the theorem. I'm using the theorem. It's written right up here. Just using the fact that the limit of f is L and the limit of g is M. Now, by a theorem about sequences, this is from section 3.2. I'll put this all in parentheses. Obviously, you wouldn't have to, but I'm just telling you. Okay? We know that if we took the sequence f of xn and we added g of xn, that would converge to L plus M. Okay. So we used our theorem from the top to convert to sequences. We used our theorem about sequences. Now we need to use our theorem from the top to convert back to functions. What does the top say? Theorem at the top says if we get the right limit for every sequence in our domain that converges to C, then indeed part 1 says the limit is what we claim. Well, did we prove that this works for every sequence? We did, because we considered an arbitrary sequence, right? We had no conditions on what the sequence xn had to be. Okay, because we've shown this for every sequence xn in A minus C that converges to C, we know, again, this is by a theorem, the theorem that we started with, that the limit of g, f plus g is L plus M. As desired. Let me zoom out just a little bit so you can get the whole thing. And I will put, we'll call this a theorem. Okay. Are there any questions about that?
So just to make sure I'm following this, so what we've done is we've used we know that two sequences, if you take a sequence that equals like the sum of those two sequences, f of xn and g of xn, we know they converge to C, and then we're using our stated theorem that that because any sequence of f of x plus g of x converges to L, then to L plus m, then the function f of x plus g of x converges to L plus m. Am I following that correctly?
Yeah, I think you said one thing incorrectly.
I think I said converge to C accidentally.
Yeah, yeah. Other than that, it's all correct.
Okay, thank you.
Yeah. Now I said we could prove this directly. But this is the proof we gave is clearly a little bit nicer because there's no epsilons. It's a good exercise to prove it directly. I think I would like to try to end this lecture on time, if not a little bit early. So I'm not going to go into a proof from the definition. Okay, it's a good exercise. Any other questions about this? Okay. Then remember what I'm saying. I'm saying that we're taking.
Daniel has a question on the chat.
Oh, I'm sorry. Yeah, Daniel. Yeah, that's what I'm about to do. Right, we're going to do all the field operations. So I said this is function versions of section 3.2 results, and that's what we're going to do. So let's remember our section 3.2 theorem. Okay. So this is our theorem from section 3.2. Now, I'm going to just write this in shorthand. This is not. I hope we all understand the difference between shorthand and what you should write in an actual proof. Here's our theorem. If xn converges to x, and I want to change that. We've got an xn hanging around, and I don't want to confuse anybody. It would be fine to have xn here, but anyway, we'll do an and bn. Then what were our things? 1 minus an converges to minus a. 2, the absolute value of an converges to the absolute value of a. 3, an plus bn converges to a plus b. 4, the product. Okay. And 5 is the trickier one. Five is the reciprocal. And I need to add something there. Sorry. It could be the case that your sequence is non-zero, but your limit is 0, like if your sequence is 1 over n. Okay, so your sequence is all non-zero and your limit is non-zero. Okay, this is what we know about sequences. So we're going to plug in. What are we going to do? We're going to replace, essentially, an by f of xn and bn by g of xn. Okay, we did that already in the third one when we're adding two sequences. That's what we just did. So we say, okay, we know that our functions converge, so if we let xn be any sequence of the right form, then the sequence of function values converge. The sequences of function values converge. So then we used this theorem, and we said we know that if we sum two sequences, that sequence converges to the sum of the limits. And then we translated it back. We said, well, okay, then we know that the limit of the functions is the same. Okay, so what are we going to get when we play this game? Theorem, it is essentially 4.2.4 in the textbook. Let's do the hypotheses first. They are our standard hypotheses. So we've got a subset A, we've got a cluster point, and we've got functions from A to R. Okay, if, I'll write these on a new line. So this is all exactly the same hypotheses as the theorem we started with, because the theorem we started with is a special, it's one of the 5 things in here. And I'm just translating all the limit things into functions until I get to the quotient. That's going to be a little bit more interesting. Okay. Now, this 5th thing, it's the quotient thing. I'm going to put in the strongest possible conditions I could put in. If, let's see, f Okay, if f of x is not 0 for all x, I could say in A, but actually I can do it a little bit better. I can say in A with C removed because we don't care what happens at C. And we've already said that the limit of f as we go to C is L, so I want L to be not equal to 0. Then the limit of 1 over f of x is 1 over L. There we go. That's the complete statement of the theorem. Are there any questions? I'm not going to prove this. We already proved part 3. Okay, all the other proofs are exactly the same. Translate the sequences. Use the theorem. Oh, I'm sorry. you guys are welcome to tell me when there are things in chat that I'm not reading. We are assuming the same domain on F and G, right? We're assuming that they both map from A to I. Okay, that does not need to be there. I mean, okay, so if you think about functions, you're probably used to thinking about like the widest possible domain that a function could have. That's the wrong way to think about it. Okay, the thing to think about with A is that if we want to take a limit at C, A is some small, and in fact we've defined this term so we could use it here. Think about A as some small neighborhood of C. Okay, it doesn't need to be a lot of points. It's just it's a lot of points near C. Okay, C needs to be a cluster point, but that's about all we care about. Okay. So we're restricting F and G to a domain A. I hope that makes sense. So in this theorem, we're assuming that they do really have the same domain because we restricted their domains.
I have a question.
Go ahead.
Isn't it enough to say that f of x equals 0 for at most a finite number of points? Because we could technically, talk about the tail.
Well, okay, so functions don't have tails.
Oh, right.
The equivalent to a tail of a sequence is if we shrink the neighborhood down in a function. Mm-hmm. So what you would do if f only had finitely many zeros, you would shrink A.
Mm-hmm.
Right? And yeah, and actually we could go much stronger instead of finitely many zeros. Because for instance, think about if f is sine x. Okay.
Mm-hmm.
And we want to take the limit of 1 over sine x. Oh, I'm sorry. Then the limit is 0. Let me just say that yes, if you only had finitely many zeros, you could shrink your domain so that you avoid all of them.
Wait, so if you shrink your domain, then how do you guarantee that C is still a cluster point? Because you need for all delta greater than 0, right? That you have some point in A.
Okay. Yeah, but you don't need that point to be delta away. It could be a lot closer than delta. So I'm saying, so let's draw a picture. For those of you for whom this is confusing, this is a tangential thing. I mean, it's a good thing to talk about, but it's a little bit tangential. Okay, we're on the real line, so never mind that picture. It's a better picture in R2. Here's the point C. Let's say our domain, let's say we've got zeros. I'll mark the zeros in red. Okay, so those are zeros of F. Okay. And let's say we kind of want our domain to be from here to here. Okay. Well, let's say C is a cluster point of that. And we want to look at 1 over F, but we're not allowed to because F is 0 inside this domain A. Okay. So what I'm saying is just come in and shrink it down to that. Okay, so that you aren't 0 anywhere in there. Now, the question was, if you do that shrinking, will C still be a cluster point? Yes, because the definition of a cluster point is if I look in any, I mean, the word to use here is any neighborhood of C. So if I look anywhere around C, I will find at least one point where in A. Okay, so if C was a cluster point before, then it's still a cluster point.
Okay, thanks. Yeah, I was messing up with the delta, but thanks.
No problem.
So what does the highlighted green area?
That's what I
Yeah,
would.
again?
That's what I would restrict my domain A to.
Okay.
Okay, so that's the discussion of that. We could shrink our domain. And that's essentially what we do. Is if we want to do 1 over something, we'll shrink it so that. Notice we'll shrink it so that we're not 0 for everything except possibly we're 0 at the point. Okay. Okay. That's the theorem. Like I said, I'm not going to prove it because we already proved one case and all the other proofs are exactly the same. Instead, we're finally going to do some examples. Number 1. We did this one. I think this was the one I did at the kind of as an added exercise at the end of last lecture. I think it caused me to go 40 minutes over. I think this was the one. So now we're just going to use the theorem. Right? If C isn't 0 and we're taking the limit of 1 over x as x goes to C, okay. Well, we're thinking about our function f of x would be x, okay, and our set A would be something like 0 to infinity. Oh yeah, let's do 0 to infinity or minus infinity to 0. Depending on where c is. And by that I just mean what side of the real line it's on. Okay, then the theorem says, well, this is just 1 over the limit of x.
Why is it important to define a here?
Right, so this gets into a little bit of subtlety. If you were solving this on homework or a quiz, I would not say it's important to say what a is. I'm just kind of saying, I'm assuming that if I didn't say what a is, someone would ask me. So I figured I would just say it first. Okay. We've talked about this a little bit. By changing the domain A, you can cause a limit that doesn't exist to exist. Okay? But you can't actually change a limit that already exists. Does that make sense? And you can go through, this isn't a deep thing or anything, you just go through the definition and you can see that. If your limit existed for one domain, and you chose a smaller domain, it's not, the value of the limit's not going to change. And actually, you can go through and you see it's not going to change, and it's not going to stop existing. However, if you have a limit that doesn't exist for some domain, you can actually restrict your domain and cause that limit to exist. Okay. Anyway, for almost all normal limits, we just assume that our domain is some small neighborhood around the point where we want to take the limit, and we're happy, and we just don't even mention the domain. Okay? So unless otherwise mentioned, you may always assume that the domain about which you're supposed to consider the function is a small neighborhood of the point where you're taking the function. Okay? Small enough in particular that there are no singularities there. There's no zeros and this kind of thing. Is that okay? Okay. Okay. Thank you, Olivia, for the thumbs up. Again, we just know this limit is c. Oh, what did I say? I'm an idiot. Okay, this limit is 1 over c, because the limit as x goes to c of x is c. Good. Two. Let's just compute some limits. X goes to 3 of x squared minus 1 times 3x plus 7. Okay? Now, think about if you were going to try and use the definition here. Okay? Your proof would start, let epsilon greater than 0 be given. And then you're going to have to find the delta that works. Okay. Now, thanks to our theorem, we say, well, that is the limit as x goes to 3 of x squared minus 1 times the limit as x goes to 3 of 3x plus 7. Because we know that the limit of the product of those functions is the product of the limits. Okay. Now, we can go even farther. Let's break this down as far as we can, okay? This is the limit as x goes to 3 of x squared plus the limit as x goes to 3 of minus 1 times the limit as x goes to 3 of 3x plus the limit as x goes to 3 of 7. Okay. Please never do what I'm about to do on a homework or a quiz. You don't have to do these things, okay? But I'm going to do it once. Okay? How would we break it down farther? I'm going to break it all the way down to basic limits. The limit of x squared is the limit as x goes to 3. That's a product of x and x. Okay, plus. But really, well, yeah, constants are fine. We know the limit of a constant. Times the limit. Okay, this is the limit of 3 times the limit of x plus now a limit of a constant.
So in like a quiz or on our homework, we don't have to be this intricate, do we?
No, I'll take points off if you do this.
Okay, gotcha.
Nah, I'm not. I'm just kidding about taking points off, but please don't do this. Okay.
Understood.
So we know the limits of x. We know the limits of a constant. We know the limit of a constant x and 7. Okay, and we're just writing them down. 3 times 3 plus 7 equals, and now 8 times 16.
So it's just like I'm discouraged, that's all, right? I understand, thanks.
Mm-hmm. Okay, good.
So just to clarify, we can take that the limit of x going to 3 of x is obvious, right? We don't have to.
We proved that. We proved that a couple, 1 or 2 lectures ago.
Okay.
Okay, so I'm referring back to that.
If it was something a bit more complicated, then we would have to then prove that.
Yeah. So, I said never do this on a homework or a quiz. Let me show you what part not to do. Never do that part. Okay. And
Makes sense. I mean, we all could just we could all just plug it in, and that makes sense.
Good. And after this quiz, you never have to do that second step. Okay. Okay. Let's do as our third example. Oh no. I don't know how to turn that. There we go. Our third example, if p of x, let's see if I can figure out how to use this again. Okay, if p of x is any polynomial, so it is a polynomial, then the limit x goes to c, p of x is p of c. So for polynomials, you can just plug in. Okay. This is the real thing that's going to save you a lot of time. This is very good. And why is this true? Well, suppose p of x, I guess we're not really supposing, we're letting it. Okay. So we're going to put in a generic polynomial. Okay, so everybody remember what your generic polynomial is. There you go. And x to the n plus dot 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 plus a1x plus a naught. Yeah, some people, and to respond to the chat, some people say that the zero polynomial has degree minus infinity, but that one's allowed too. But we are not, yeah, so polynomials don't have terms of the form 1 over x or 1 over x squared or these kind of things. They don't have those kind of negative powers. Negative powers, that's what you meant to ask, and no, they're not allowed to. Okay. Then, using our theorem, what would we say? The limit as x goes to c of p of x is the limit. I'm just going to substitute in what is this thing? Equals. And now, what is it? I'm going to use the theorem. an times the limit as x goes to c of x to the n plus dot 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 plus a1 limit as x goes to c of x plus a naught. Okay? Now, if you really insist, perhaps a better example right before this one would have been, we could have shown that the limit of just x to the n as x goes to c is c to the n. We could have shown that. But I hope you'll agree that that follows from the same theorem, right? Just doing products. Instead, we did additions before. Oh, and I guess I did do products to pull the scalars out. But there we go. Theorem shows that limit of polynomial is polynomial at that point. Okay, now there's, where do I have 6 minutes left. There's a couple things I want to do. All right. Okay. Here's an example. I'm going to take this straight out of the book because I know I didn't make my own, and I know the division will work out. And it's important the division does work out. Say we want to compute this limit. Can we use the theorem?
Yes, because it's just, it's just, oh no, yeah, right, we can't.
We can't because we can't do this denominator, right? That the denominator is okay. Well, the problem actually isn't the fact that the denominator is 0 at 2. The problem is the fact that the limit as x goes to 2 of the denominator is 0, right? So if you try and use the theorem, here's what you'll get that's wrong. You would get that it's the limit as x goes to 2 of x squared minus 4 over the limit as x goes to 2 of 3x minus 6. Okay. You'll get 0 over 0. Okay. So what do you do in this case?
Factor out x minus 2.
Yeah. So what we'll do is we'll say we have our function that we care about is an x minus 2 times an x plus 2 over a 3 times an x minus 2. Now, what I'm going to write, I'm going to write some words above this, okay? But they're not here yet. Where is that statement true?
X is not 2.
Yes. Okay. At 2, those two functions don't agree because the one on the left is not defined, but the one on the right is. Okay? But here's the thing. When we're taking a limit, the point where we're limiting to is precisely the point we don't care about. Okay? So so since we don't care about that point, we don't care about what it's defined to be at 2. It will be exactly the same as the limit of this thing. And now by the theorem we see that that's just 4/3. Okay. We good? It's another way you could have done that.
Brings me back to the days of regular calculus, or maybe algebra.
Yeah.
Even,
So
yeah.
what's another way you could have done this back then?
L'Hopital's rule?
Yes,
However you say that, yeah.
L'Hopital's rule. Yep. We're actually not going to do L'Hopital's rule in this class because here's a meta theorem. There is always a better thing to do than apply L'Hopital's rule. Okay. In this case, the better thing to do is to just factor out the root. Okay. What would we do if the root didn't factor out? Yeah, that's the whole thing. If the root doesn't factor out, then the limit's not going to exist because the function's going to be unbounded in that neighborhood. Okay. So you'd be able to prove that it gets, Okay, I want to do one final thing, and I'm just going to state this thing. Squeeze theorem, I don't think we did this for sequences, and we really should have, but let A, I'm just going to state it for functions, let A be a subset with cluster point C. Let's have 3 functions, F, G, and H, with domain A. Here's your statement. If you have this inequality, then the limits okay. I'll state it in the squeezy way here. If you have that, and you have this, so you have the limits on both sides being the same, on both the small side and the large side the same, then the one in the middle is squeezed, so it has to have that limit. That's the theorem. Okay. The way you prove it is you go back in time to when we considered sequences, and you prove the squeeze theorem there, which is not a difficult proof, but we didn't have time for it in that lecture. And then you can just translate the squeeze theorem the way we translated those other things about sequences to things about functions. Okay, so that is section 4.2. Basically just lets you take limits the way you want to. I'll stop the recording, but I'm happy to stick around for